Let us now sketch the graph of f of x equals x cubed minus 6x squared plus 12x minus 5. Okay, and so the first thing we're going to do is take the first and second derivative of the function. That will give us f prime of x equals 3x squared minus 12x plus 12. And then taking the second derivative, f double prime of x, we get 6x minus 12. So now to find critical points, we are going to set our first derivative equal to 0. So we're going to let f prime of x equal 0. Okay? And this is to find the critical points. So in doing so, we have 3x squared minus 12x plus 12 equals 0. And so we'll solve. We can divide both sides by 3. So we'll have x squared minus 4x plus 4 equals 0. And so that is just the perfect square binomial, x minus 2 squared, 0. And so we get a critical point at 2. Okay, so we know we have a critical point at 2, and we want to find what the value of f is at 2. So we'll know what point to plot on our graph. So let's find f of 2. So plugging 2 into our function, so everywhere we see an x, we're simply going to replace that with 2. We find that f of 2 equals 3. Okay, so we can go ahead and get started on our graph by plotting 2, 3. All right, and now we need to set about trying to figure out what's going on at that critical point. So we're going to look at that second derivative. So we have 6x minus 12, right, for our second derivative, and we're going to evaluate that at our critical point. So we need to find f double prime of 2. And we get 6 times 2 minus 12, which of course is 0. So that means there is no extrema, right, because the second derivative test is inconclusive when we get a value of 0. Okay, so there's no extrema, right, for this function, but we do have a possible inflection point. Let's write that down. Let's see, inflection point possible. And so to determine, we're going to look to the left and right of 2. So we're going to look at, what is our function doing in terms of concavity immediately to the left of 2. So, maybe we want to take into account 1.999. So we're just to the left of 2, and we find that when we evaluate that, we get a negative value. When we go to the immediate right of 2, okay, then we find that that value is positive, right? And so because we have a change in concavity there, we know that there is an inflection point. So since there is, again, a change in concavity, with this one we have concave down, here we have concave up. So we can go ahead and get a graph going. We do want to plot some additional points to get a more accurate graph. One kind of easy point for grabs here is the y-intercept is -5. So we have 0, -5. And so here we know that we come up, and if we want to find the x-intercept, we certainly can, but there's our point of inflection right there at 2, 3. So we have 2, 3 is on the graph, and 0, -5 is on the graph. Okay, one more example where we use the first and second derivative test to graph a function. This function is one that has no critical points, so let's take a look. Let's say we have f of x equals 1/6 x cubed minus 3/2 x squared plus 5x plus 1. Okay? And so we are going to then look at our function f of x, and we are going to take the first derivative. So we're looking for f prime of x And in calculating that, we get 1/2 x squared minus 3x plus 5. Okay, and we'll go ahead and find the second derivative. So the second derivative is x minus 3. Okay, so now let's set the first derivative equal to 0 to get our critical points. So we're looking to get our critical points, so we're going to let the first derivative equal 0. So we have 1/2 x squared minus 3x plus 5 equals 0. We'll multiply through by 2 to eliminate the fraction. So we have x squared minus 6x plus 10 equals 0. So here we see the quadratic is not factorable on the left. So we can apply the quadratic formula and see what happens. So we have 6 plus or minus the square root of b squared minus 4ac all over 2a. And so we see here that our discriminant is going to be negative. And because the discriminant is negative, then the first derivative is never 0. Okay, so here we have a negative discriminant. So our first derivative is never 0. So that means there's no critical points. Okay, even though there are no critical points, we still want to be able to graph it, right? So we can move along now to the second derivative test to look at concavity. So now looking at the second derivative is x minus 3. And we can look immediately to the left of 3, at 3, and then to the right, okay? And so here we have 3 cases. X is less than 3, x equals 3, right? And at x equals 3, of course, that's significant because it means that f double prime would be 0. So that would mean that we would have a possible inflection point. But to verify that that's an inflection point, we need to look at what's going on to either side. So for values that are less than 3, like 2 or 1, right? Any value that you look at for x that's less than 3, you see that you have a negative result. If you look for values of x that are greater than 3, like 4, 5, 6, and so on, you'll see that you have a positive result. And so because concavity changes, we know that we have a point of inflection. And so that helps us greatly. And so this problem is similar to the last one, but again, it is different in that we didn't have a critical point there. So we can graph using our information that we found. Okay, so plugging in 3 into our function f, we find that f of 3 is 7. So we can plot that point on our graph. So we have 3, 7. We need another point. We know that this is a cube function, and so it has the basic shape of a cube, but we need a little bit more precision. So we can find the y-intercept very easily, right? The y-intercept is when x is 0, so we know that that happens at 1. And we know that for x is less than 3, we're concave down. And for x is greater than 3, we are concave up. So that will yield this graph. Now we could always get more points to plug in to make the graph more comprehensive, or you can simply just draw a tangent line at the point 37. So to do that, what you would do is just look at your first derivative. So you look at this and just evaluate that at 3, and that will give you the slope of the tangent line at 3. So if we do that, if we find f prime of 3 and we plug a 3 in where we see an x, we'll get a half. That means the slope of the tangent line at 3 is 1/2. So you can kind of over 1 up 2, right? And so that tangent line would be like right there. And that does help you get, a little bit clearer picture of what's going on. So that is one way to make your graph more precise. Again, is to just pencil in that tangent line for your graph.